Hello everyone, welcome back to my channel. So in this video we will see about boundary layer theory, and also we will see various thickness related to boundary layer theory. So coming to the introduction part, boundary layer theory is basically found by L. Prandtl in the early 1900s, to say exactly around 1902 and 1903 around. So this is not a new concept actually, this is what we experience in our daily life. Moving on to the definition for boundary layer. So boundary layer is the layer of fluid which is accumulated or which is formed around the surface of a body or surface of a we actually say it as a surface. Here surface means it is the surface of a body. So when there is a body which is at rest, or maybe when it is at moving, in either of the cases, when a stream of fluid, whether it could be air or water, I mean to say liquid, if the fluid stream passes over the uh, or touches the surface of the object or the boundary, basically at the boundary of the surface or at the boundary of this object, a layer of the fluid will be accumulated, and this uh, velocity in this region which is surrounding the entire surface of the object or the body is called as boundary layer, and the velocity in this boundary layer is zero. And as we move away from the surface of the boundary layer, automatically the velocity of the fluid layers increases and it matches with the free stream velocity, because the velocity of the fluid which is attached to this surface will be zero, and above that little velocity it may have. So as we move upwards, as we move away from the surface of the object, the velocity matches with the free stream velocity. Coming to the characteristics of a boundary layer or a flat plate. So let's imagine a flat surface, and how does the boundary layer behave on this flat plate is we will see now. So for this explanation I have taken the example of this figure. So if you see here, this is our boundary layer. Okay, boundary layer, I'm sorry, it is our surface. This is our the one which is colored here is a flat surface, and on this flat surface you see point A. The point A is the leading edge, means here this is the starting point of the plate, and you see velocity, with the velocity of u the stream is flowing. So a fluid stream is flowing over this flat plate. So we will see, once this fluid of velocity u is flowing on this flat plate, what happens we will see. Okay, so if you see near the leading edge, means at the beginning, if you see, the basically the formation of the boundary layer thickness is very small, because initially the fluid stream is coming from this side. So once it touches the surface and it starts flowing over the surface, very few molecules starts adhering, or very few molecules start losing their velocity, and hence from A to B, if you observe, or it is said that up to this zone, since the formation of the boundary layer is just starting, and the thickness of the boundary layer is very small, this zone is said to be a laminar zone, and the boundary layer which is present in this zone is called as a laminar boundary layer, because the fluid still follows a laminar flow in this region. But as we move forward, it is shown, the laminar boundary layer LBL is shown by the curve AE, and the region is from A to B. But as we move forward, what happens is that the thickness of the boundary layer keeps increasing, because when we are moving forward from this point B, there is still fluid coming continuously from this side. So already the molecules start adhering near the surface, and still fluid is continuously flowing from backside. So what happens, the thickness of the boundary layer keeps increasing. Okay, from B the thickness of the boundary layer starts increasing, and what happens here is that suddenly the laminar boundary layer becomes unstable, because as I've told, there is fluid coming and striking from behind. So what happens, it changes its shape into a irregular motion, means it's trying to convert. So if you see the same figure, till AB it was laminar, and now since the fluid is continuously coming, what happens, this laminar boundary layer suddenly changes its nature, and it becomes it starts becoming turbulent. So this change of zone from laminar to turbulent is called as transitional zone or transition zone. Okay, and if you see this picture, it is represented by the zone BC, and EF is called as transitional boundary layer. So in this zone, the boundary layer is neither laminar nor turbulent. But again, as we move forward, the uh, boundary layer further changes to turbulent, because transition zone is for a very short period. Since the movement of fluid is continuous, since the layer of boundary layer thickness is continuously increasing, it would finally end up with a turbulent boundary layer. And this turbulent boundary layer is represented from the figure by FG. So here there is G, so it is represented by FG or the zone CD. So from C to D, the fluid will be under turbulence, and this layer is called as turbulent boundary layer. So the talking about concept is easy, but practically how to know whether the liquid is in laminar zone or whether the liquid is in turbulent zone. So for this only, we'll take the example of Reynolds number. So what does Reynolds number say? So you can watch my earlier videos where I talked about Reynolds number. So Reynolds number says that uh, for see, Reynolds number for pipe flow will be different, Reynolds number in open channels will be different, and for boundary layer concept also Reynolds number will be different. Okay, so if you talk about pipe flow, we say Reynolds number, if it is less than 2000 it is laminar flow, it is greater than 4000 it is turbulent, and if it is in between it is transition. This is for a pipe flow. But if I talk about open channels flow, Reynolds number is less than 500 only, we call it as laminar flow in case of open channels. Okay, so like this, if you talk about boundary layer, here our Reynolds number for boundary layer for a laminar zone will be equal to or less than 5 into 10 power 5. So one has to remember this value, 5 into 10 power 5. So how to calculate that Reynolds number? I told you the boundary layer will be laminar when Reynolds number is less than or equal to 5 into 10 power 5. Okay, this is fine. But how to calculate Reynolds number? So Reynolds number is given by this formula. It is U into X by nu. So what is U? It is the stream velocity, with which velocity the fluid is moving. And X stands for the distance from the leading edge, means from the starting point at how much distance we are going to check our boundary layer, means how the nature we are going to check, X meters. And nu is the kinematic viscosity, which will be given as in Stokes. So if you substitute these three values, you'll get the Reynolds number. Check whether the Reynolds number is less than or equal to 5 into 10 power 5. Then you will understand at that particular distance of X whether your boundary layer is laminar or not laminar. Okay, so this is about boundary layer characteristics. Now we will just quickly look into the various thicknesses related to boundary layer. So anywhere you see people talk about these four thickness. One is boundary layer thickness, displacement thickness, momentum thickness, and energy thickness. These are actually very important because we will be solving problems on this, and they are continuously asked. People continuously ask in question papers like what is displacement thickness, write the formula for it, etc. So let's see what are the thickness related to boundary layer now. First of all, what is boundary layer thickness? So boundary layer thickness, it is the distance from the boundary of the solid body measured in y direction to the point where the velocity of the fluid is approximately equal to 0.99 times the free stream velocity. So let's say this is a flat surface and he is telling it is in y direction, means in this way, in a perpendicular direction to this is our plate, let's say, or surface. So in y direction, the layer or the point where the velocity of this layer is approximately 0.99 times velocity of stream, that is u. Means 0.99 times means what? Almost equal to u. So this distance from the surface to the layer where the velocity of that layer is equal to the velocity of the free stream, then this thickness only is called as boundary layer thickness, and it is denoted by the symbol delta. And let's talk about the next one is displacement thickness. So displacement thickness is also measured in y direction, like this is our surface, then it is measured in y direction. Okay, depth. And it is the what is the definition of this is that it is the amount by which the boundary layer should be displaced to compensate for the reduction in flow rate on account of boundary layer formation. So due to the boundary layer formation on the flat surface, we may lose some discharge. So how much amount of boundary layer, how much amount of boundary layer I should remove such that I can compensate this loss of discharge from inflow to outflow is called as our displacement thickness. So how much I should displace the boundary layer so that my loss of discharge is recovered is called as displacement thickness. It is denoted by delta star. The formula is 0 to delta 1 minus u by u into dy. And next comes the momentum thickness. So momentum thickness is very similar to displacement thickness. So in displacement thickness, I told the amount or the quantity by which the boundary layer has to be displaced to compensate what rate of flow. Here it is compensating the momentum. Okay, remember, for momentum thickness it is compensation of momentum, means because of the formation of the boundary layer, what is happening, I may lose obviously the particles or the molecules in this boundary layer having low velocity and sometimes zero velocity, because the molecule which is closer to the boundary surface is having zero velocity. So I am losing velocity. When I am losing velocity, I am losing momentum. So how much amount I have to remove this thickness so that I get momentum equal from inflow to outflow is called as momentum thickness. It is denoted by theta. The formula is 0 to delta. If you remember, this formula is very close to the earlier formula. Here it is 1 minus u by u dy. Here it is u by u into 1 minus u by u dy. Yes, and the last one is energy thickness. So in energy thickness, we are going to compensate the reduction in kinetic energy. So from the surface, how much amount of boundary layer I have to displace so that I can compensate the kinetic energy at the inflow as well as at the outflow. So this is called as energy thickness, and it is denoted by the symbol delta double star, and this is given by the formula delta star star is equal to 0 to delta u by u into 1 minus u square by u square into dy. So if you observe, all the formulae are related to each other and close to each other. It's quite easy to remember. So boundary layer thickness is to compensate the rate of flow. uh, Boundary layer thickness is the thickness where the velocity of the layer is 0.99 times the free stream velocity. Displacement thickness is compensating the rate of flow. Momentum thickness is compensating the momentum. Energy thickness is compensating the kinetic energy. So this is all about the various thickness related to boundary layer. So in my upcoming video, I'll do a numerical problem related to this three thickness, that is the energy thickness, momentum thickness, and displacement thickness, which is a very frequently asked question. Okay, so hope you all understood the video. Thanks for watching.